Hello, everybody. Xavier Velez here again for chemistry, and we're getting ready for our seventh week here. And today we're going to be talking about the VSEPR field theory. So, without further ado, I'm going to start with the presentation of our electrons and molecules. To begin, there are different electron domains that will have different molecular geometries based on the bonds and placements of their lone pairs. Electron domains refer to the arrangement of electrons, including bonds and lone pairs, around a central atom, whereas the molecular geometry explains the arrangement of the actual bonded atoms. Okay. With that being said, when there are no lone pairs around any of the central atoms, the molecular geometry will be the same as the electron domain geometry. So for today's presentation, I'm going to be discussing the types of molecules using hypothetical terms AB in order to describe the electron domain geometries. So let's begin. Here we have molecule AB2. AB2 is linear in that it is a straight line. There's no other real shapes to it. We have A, which is in the middle, and we'll pretend we can see it. It's the center point here, okay, holding the two B's together. So we have A in the middle and the two B's, and this is a linear example using balloons of this molecule. Okay, in a molecule AB2, we could have either 3, 4, or 5 electron domains. So just remember that. Okay, so AB2 with 3 electron domains will have a trigonal planar shape, and an example of that would be sulfur dioxide, and it will have 1 lone pair. So let's look at a trigonal shape. That is, hand that to me. Thank you very much. This is trigonal, or trigonal, as I've heard some people say. So it is 3 together held by your center A atom in the middle. Okay, so there it is. This is your trigonal shape. Okay, so with 3 electron domains, and that's that. AB2 with 4 electron domains will take a tetrahedral shape, and an example of that would be water. Okay, and that has 2 lone pairs. So let's take a look at what a tetrahedral shape might look like. Okay. And here we have tetrahedral. Looks very similar to the last one, except there is a 4th one here. Okay, so you can see kind of wraps around, and you can try to squeeze this together and put them 4 side by side, all right, sharing 90 degrees each angle. But if you hit them and bring them back, they automatically go back to this type of shape. Okay, so this here is water. Okay, another molecule with 4 electron domains, and can also be described as AB3 as well, and having the same shape, tetrahedral, okay, is ammonia, right? NH3 with 1 lone pair. Okay, AB2 with 5 electron domains will have a trigonal bipyramidal shape. An example of that is iodine fluoride with 3 lone pairs. So let's find what that looks like. And that one here, I'll back up a little bit. You can see it. We have 3 and 2. Okay. So this is trigonal bipyramidal. Okay. Lots of balloons here. Okay. And again, there is also AB3 with 5 electron domains and having a trigonal pyramidal shape, and that's chlorine trifluoride with 2 lone pairs. So lots of different ways we can make these configurations depending on the atom and arrangements. Okay, and then the last one we want to mention here, AB4 and AB5 can have 6 electron domains, like xenon tetrafluoride, and bromine pentafluoride, which will both have an octahedral shape. All right, so let's see if we can make this happen. So octahedral shape. Get one more. this here. Whoa. Sorry about that.
It looks like it's gonna break.
No.
That was an accident.
Yeah. So it'll essentially look like the bipyramidal one, with the exception that there's 4, and then the 2. Okay. I think we got them all covered. This last one here is the octahedral shape. And that's that. So the balloon geometry is representative of the electron domain geometry, thus creating 4 models representing the 4 different shapes: trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Having the molecular formula alone is insufficient to predict the shape of the molecule, though. So we just have to be very careful. For instance, AB2 molecules may be linear or bent. They could be both, right? AB3 molecules may be planar, pyramidal, or T-shaped. So just because we know, the molecular formula doesn't necessarily tell us which shape it's going to be in. Okay. So to determine the shape, though, we must start with the correct Lewis structure and apply the VSEPR model to it. Okay, and that's what helps us determine which shape and arrangement this molecular structure will be in terms of physical representation. Thank you very much. Have a great day.